All right, number 14, classify the response to each of the following questions as quantitative or qualitative. Okay, quantitative or qualitative. I think I'm going to switch the columns here, just a minute. All right, so quantitative basically means these are numerical values that can be calculated or manipulated in a meaningful way. And qualitative basically means it's non-numbers. Now, I know this is not exactly right because sometimes the qualitative piece of information or data can be numbers, okay? But these are the types of numbers that you can't really calculate in any meaningful way. All right, for instance, if I ask you for your ID number, everybody has an ID number, just list all those ID numbers. All you see are numbers, okay? But that's not quantitative data because you take the average of ID numbers, it doesn't really mean anything. So that's not a meaningful calculation, right? So I hope you understand. Qualitative is anything that cannot be computed in a meaningful way. All right, so in what state do you live? Okay, clearly it is qualitative, okay? Qualitative because it's not a number. How many years have you lived there? That's quantitative because it's a number. Let's go ahead and put the number sign here, right? And because you can, for instance, find the average number of years that people lived in their places and so on. How old are you? Okay, again, you can talk about the average age. So that is a number and that is quantitative information or quantitative data. What is your occupation? All right, so what do you get when you divide a nurse and a policeman and a teacher by 3? Well, you can't do that, right? So that's qualitative. And then what is your favorite type of music? Okay, you can again take classical and pop and jazz and rock and divide it by 4. And you have indie music or whatever. No, you can't do that. So that's qualitative. All right, so that should be pretty straightforward. Okay, no problem. I'm not going to say anything more here. What is a placebo? Right. Now you could say, and have had students saying it's a sugar pill. Okay, well that's okay. I would personally like to say something like a treatment or medicine or pill without active ingredient. Right? And the reason is because sometimes a placebo is not a sugar pill. It could be water if the real treatment looks like water, and so it's a treatment or a medication without active ingredient. You can say ingredients if you like. Right? That's what a placebo is. Now, what is placebo effect? What is a placebo effect? Okay, this is the effect of improvement based on the psychological effect, right? Psychological effect by believing that the treatment works. Now, I have a slightly different version of this answer here. In the typed up version of the answer key, what I have written there is that a placebo is a fake treatment, often a sugar pill, without an active ingredient given to the control group. It is important to, note here that this is given to the control group because the other group is getting the real treatment, right? Like a real vaccine being invented or being in development or something. Now, the psychological effect I'm talking about is, sometimes a patient will feel like, what, I am taking this medication, I should be getting better. And that psychological effect, the placebo may actually help the person improve the conditions. This is called the placebo effect. Sometimes people do get better if they think they are getting treated. And the reason they, put a placebo is because maybe the placebo is what's working, not the medication itself. Maybe not the active ingredient is not really doing anything. If the same improvement is observed both in the control group getting a placebo and the treatment group, then you say, what, the improvement is not based on the treatment. It's based on their psychological effect. So that medication or that treatment will not be considered effective if the placebo does equally as well as the actual treatment. I mean, interesting thing, sometimes the placebo outperforms the real treatment. You know, there's been like the hair growth kind of a medication that was developed, and the people taking placebos were actually doing better than the ones getting the treatment. Obviously, that new medication did not get approved. All right, number 16, explain the difference between a single blind test and the double blind test. All right, it's going to take some time. Let me just write this and then I'll come back to show you what the difference is. I hope maybe you can write down or explain the difference between the single and double blind test to yourself and come back to this. I will pause this for just a little bit and then come right back. All right, so the difference is this. In both of these tests, a placebo is definitely used, okay? So one thing you should remember first is that in both single blind test and a double blind test, definitely a placebo is used, okay? The question lies in who knows which patients belong to the placebo group or control group, and then which patients belong to the treatment group or the group getting the active ingredient, right? And in the single blind test, patients are the only ones who do not know, okay? So obviously patients shouldn't know they're getting a placebo because that would kill the whole purpose of using the placebo. But in this single blind test, the patients do not know if they are in the treatment group or the placebo group or control group. But the doctors or the evaluators know because the assessment, the evaluation is something very objective, like maybe the fever or the heart rate or the cholesterol level, or something very specific, right? But the double blind test is where neither the patients nor the evaluators know which group the patients belong to. And that is necessary. Sometimes the evaluators should not know which patients belong to the treatment group and control group because that may influence or affect their evaluation, right? So you remember the example of an antidepressant medication, for instance. If the evaluator knows that this one particular patient is getting a fake pill, the evaluator, he or she may think, okay, this patient can't be getting better. So subjectively, the evaluator may decide that the patient is not getting better because the evaluator just happens to know that that particular patient is getting a fake pill. So in order to avoid that kind of a bias in subjective evaluation, maybe a double blind test is necessary. Okay, so I hope you understand the difference between a single and a double blind test. This is much more careful and therefore much more expensive to perform or to conduct in a typical lab. So unless there is a definite need for a double blind test, they don't carry this out, but sometimes it is necessary. Okay, number 17, in the normal distribution, what is the probability that the value is? Okay, remember what the normal distribution looks like? Yeah, who can forget, right? It's a bell-shaped curve. Below the mean is right here. Below the mean, by symmetry, it is 50%. Or the probability is 0.5, okay? Exactly half of the population is to the left or the below the mean. Above the mean, but one standard deviation of the mean. So what is the probability? Let's use a different color for this, maybe green for this. What is the probability that the given value is above the mean, but within one standard deviation? Okay, that's mu. See, mu is the mean, right? And mu plus sigma is one standard deviation above the mean. So what is the probability that a random value is in this green area? Okay. Now, remember, to answer this kind of a question, we refer to the z-score. Mu has, by definition, the z-score of 0. Okay, that's what z is equal to 0 means. That means that the value is exactly the mean. Now, if you have one standard deviation about this value is one standard deviation above the mean. So the z, again, by definition is 1 because z measures how many standard deviations above the mean that particular value is. Okay, so what we are doing is trying to find the probability or the percentage of data values in this green area, right? Okay, you may actually remember this answer. But if you go, and I will be providing you with this information, where is that? right here. Okay, I will be giving you this table on the actual test. And so you look at, remember, if it's 1, you look at this number here, and the answer is 3413. And so by looking at that, you will be able to answer. This is 34.13% or 0.3413. Either of these will be acceptable. Okay, so you may have to look up some numbers in the table. Now, if you are to go to the back of this document, which I provided, in addition to this thing, which you see in the book, I'm also providing you with the more extensive table, which you'd used in some of your homework problems. And I hope you know how to use that. I think we'll be using this a bit later. Okay, so we have more to go here. All right, number 18. Let's go back to my red ink. To conduct a study, a student opinion survey about at College of the Canyons, a researcher collected samples in the following way. Identify a type of sampling used. Remember, we had, like, I think we learned 4 different ways of sampling. Picking every 100th name. As soon as you see 100th or 50th or the 10th, you say that's systematic, okay? Systematic sampling, that's it. Picking 50 male students and 50 female students, all right? So now we have classified the entire student body into males and females, and then you pick 50 of each, right? Remember, this is called a quota, and as soon as you divide into subpopulations and you pick some from each of these, okay? This is called stratified. Stratified sampling, right? And then if you picked 100 personal friends taking classes, just personal friends, that would be convenience. Convenience sampling is whatever is convenient for you. Your personal friends are the easiest ones to reach, and you don't make a whole lot of effort. And sometimes that's the only thing you can do, but it is probably not the best way to collect a unbiased sample. All right, let's go to number 19. We are trying to find out how many hours the American people spend watching TV every week. So a researcher carefully chose, I'm not sure how, but chose 1,000 Americans from all over the country. Okay, because you don't want to avoid a geographical bias, and discovered that on average these people spend 41 hours watching TV every week. All right, what was the population? Oh, by the way, when you read questions like this, you have to start asking critical thinking questions, like, what do you mean by TV? Now, of course, that may be simple, but does it include, for instance, things that you see on like different devices? Does it have to be TV programs available only on TV? How about Netflix? Netflix. How about YouTube videos and that kind of things? Right? Anyway, just be critical, and be careful, and try to be analytic as you read anything in these days. What was the population? Right, so the answer really comes from the first line here, because it says the question says to find out how many hours the American people, right? American people, theoretically all of the American people. That is the population, okay? And the population is the group of people or the things that the researchers are interested in, okay? What is the sample? The sample is the 1,000 Americans chosen from all over the country. Okay, that is called the sample. Now this is singular. Okay, you don't call each of these 1,000 people samples. Okay, or you're a sample, he is a sample, she's a sample. No, that's not the way it works. The sample, one singular word, means the group of all of these people, 1,000 people. That's your sample, singular. What is the parameter? Okay, well, the parameter is the real answer to this question, the real number of hours they watch TV. The American people watch TV every week. Okay, that's the real answer, which you will never know. So the parameter is something that we want to find out, but I mean, realistically, we will never be able to find out for sure. But there is a statistic that would allow us to estimate the parameter. And the statistic is, in this case, 41 hours a week. So that is the average that we calculated based on the answers from these 1,000 people. All right, so I hope it makes sense. Make sure you know these terms and the difference between, for instance, the population and the sample, and then the parameter and the statistic. All right, so I realize that this is not just organized in terms of chapters, because now we are about to go back to a question from chapter 4, probability chapter, but that's okay. You draw a card and then you roll a die. What is the probability that you get a spade and a 1, right? So remember, these are called independent events because the die roll is not influenced by in any way by a draw of the card. Now, what is the probability that you get a spade? Well, there are 13 spades in the 52 cards, right? And of course, that's 1/4. Right? And you multiply this by the probability that you get a 1 in the roll of a die, which is a 6, right? So this is 1/4 times 1/6, and the answer is 1/24. And this is just a question about, independent probabilities or independent events. The probability of 2 independent events, you just multiply the probabilities. Okay, a coin is tossed 3 times, right? So you have 8 outcomes, remember? All right, find the probability that you get 3 heads. Okay, so how do you get 3 heads? H, H, H. That's the only way. The only outcome out of the 8 possible outcomes, right? So the answer is 1/8. And so that should be a pretty simple question. All right, number 22, you are to create a 3-letter personal code using alphabet letters, okay? Except you can't use a Z. Now, this is a hard question because there's a restriction on this. But, and that's, by the way, that's why I don't often teach formulas. For an advanced math class, I teach formulas and we do a bunch of algebraic manipulations and all that stuff. But for these, what you have to have is critical thinking skills, right? So try to apply your critical thinking skills to solve a problem like this. Because really, life's problems are complicated, right? You don't have formulas. Okay, 3-letter personal code. So you have this, alphabet letters like A, B, C. P, Z, T, whatever, right? Oh, you can't use Z. So then what? You can use Z in any place, it sounds like, right? Except you can't use Z. How many 3-letter codes are possible? Letters can be repeated, okay? So I can say A, for instance, right? That would be fine. 25 choices because I can't use Z, right? So if you choose one of the 25 letters for the first one, how many choices do you have for the second? Well, if repetition is not allowed, you only have 24 to choose from, but repetition is allowed, so it's 25 again. And for the last one, you have the choice of 25 letters. So it turns out to be 25 cubed, and that is 15,625 different ways. All right, so that's how you can apply a slight, your ability to think and adjust your thinking in a slightly different kind of a problem. All right, now number 23, I will be asking you a question like this, as well as 24. You have a couple of tables on your test. And the reason I do this is because I believe both of these questions are important. One has to do with the conditional probability, and the other one has to do with false positives and false negatives, which are also about conditional probabilities. Okay, so make sure you know how to do these problems, okay? These are probably not going to be multiple choice, maybe, but you need to actually fill in the blanks and do your calculations. The table below shows the number of kids at a certain school who can and cannot swim, okay? So you have boys and girls, can swim and cannot swim, the total, right? What is the probability that a child, whether boy or girl, can swim? So we're thinking about total, right? So this is what you should be looking at when for part A. Out of the 140, how many of them can swim? What is the probability that a child can swim? And can swim is 90, right? So this is 9 out of 14. That is your answer. You can also do 9 divided by 14. That's like 64.3%. But you don't have to have this calculated. I would fully accept this. That would give you full credit. In fact, in a sense, this is better, okay? Because this is just approximation. All right. let's not use parentheses. What is the probability that a child can swim given that the child is a boy? So now we are going to restrict to this line, okay? Because this is the whole universe now. The question has to do with, given that it's a boy, right? So we are not concerned about the second or the last row here. These can be ignored for part B. Out of the 60 boys, what is the probability that a child can swim? You have 40 boys that can swim out of 60 boys. So that's 2/3, and that is your answer. Okay, again, easy, right? I mean, calculations are easy. You just have to know which ones to divide by which problem and which number to divide by which number. Okay, before I take another break, I want to make sure that you can get this kind of a question here. I know this is hard. Many of the students are asking me questions. Hey, I have no idea how to do this. So follow along as I do this. I will show you step by step how to fill in the each slot here. Okay, complete the table below. Let's assume now that 2% of the people have some rare disease, certain type of cancer. Okay. Only 2% of the population. A lab test is 90% accurate in identifying those who have a cancer or who does not. So the 90% accuracy in both identifying the test positive and test negative. Out of the 1,000 people, all right, so this is how you start. Now remember what I said in the lecture video? This problem is often taught using this very complicated theorem called the Bayes formula, all right? And it's really difficult. And then people saying, you know what, if you start with a certain number of people, like 1,000 or 1,000,000, it's a lot easier to write down all these answers, okay? And so it's like, wow, this is great. So this is the best way to figure out these conditional probabilities, like the probability of false positives and false negatives, right? Start with a round number, nice number, like 1,000. This problem will give you the number. I will probably give you the number to start with. So starting with 1,000, okay, I'm going to list here, number one, this number is given. What is given? The total of 1,000 people, okay? That number is given here. And then you find out the rest of this. The first thing to fill out are these two columns here, number 2 and number 3. How many of these people have cancer? This rare type of cancer. You're given 2%, right? So this will be 2% of 1,000, and that's 1,000 times 0.02, okay, 20. Number 3, by the way, number 3, you can just do a subtraction. 1,000 minus 20 is going to give you 980, because 980 people, according to this 2% rule here, is without cancer, right? Or you can do 1,000 times 0.98. That's 98% of 1,000 people. That's a 980 people. That's the same thing, okay? Now, number 4, then let's go to, and you can go to this point or this or this or this. I think let's go from the top left corner because we read from top left. Okay, number 4, how many of these people, remember, this is the first column, so we are only thinking about these 20 people who actually have this rare type of cancer. How many of them will test positive? Well, the problem says 90% accurate test. So 90% of these people, let me go ahead and write this. 90% of 20 people will test positive, because that's what the problem says. 90% of these people with cancer will be actually and accurately tested as having this cancer. So so this is, okay, let me go ahead and write in this way. It's 20 times 0.9, that's 18. Okay, so this number is 18. All right, number 5, you can simply do 20 minus 18, because if you have 20 people total and 18 will test positive, only 2 will test negative, right? Or you can think of this as 10% of 20 people, because remember, out of the 20 people who have this cancer, 10% of them will be inaccurately, erroneously, will test negative. And that's 2 people, 10% of 20 people, okay? All right, number 6, where do you want to go next? I personally go to this one. And you can do either this box or this box. But let's go to number 6 here, because test negative. So remember, these people don't have cancer. And 90% of these people will correctly be testing negative, right? So this would be 90% of 980, right? So that would be 980 times 0.9. And if you calculate this, you will get 882. 882 people out of 980 will be testing negative, and that is the correct diagnosis, right? Now, once you find that, then you can do 980 minus 882, and that is 98, and that's your number of people who will test positive despite the fact that they do not have this cancer. Or you can do 10% of 980. Remember, because 90% of these people will correctly be diagnosed as not having cancer, but the 10% will test positive, okay? And that is called false positive. This is the false positive, okay? And so, that's what you get. And so because this number is large, 10% of that is still a large number. All right, now the rest is kind of easy. I am maybe going to use a different number here. This is just a total, 18 plus 98, and that would be 116. Here, it's 2 plus 882, which is 884, right? So here, it's easy. And make sure that this plus this is equal to that, which it is, okay? If you add 116 to 884, you get 1,000. All right. So that's the answer. Now, the question is find out how many people will test positive. The answer? That's the number of people who test positive. And how many of them will actually do have cancer? 18, right? So 18, only 18 of the 160 testing positive. Okay, in other words, 116 people will be shocked to find out, hey, I test positive for this rare type of disease or cancer. But out of 116 of them, only 18 of them will actually be with cancer. Almost 100 people will be without cancer. That's 98 people with false positive. So only 18 of the 116 people who testing positive actually have cancer, right? And so this is what happens when the disease is rare. Because these numbers are lopsided, the number of false positives is tremendously large. And so, you have this alarming thing that you don't have to worry about this. I mean, certainly you should take care and you should get further testing, but you can't just assume that you have this cancer just because you test positive. All right, so I think maybe it's a good point to stop and get something to drink or whatever. Come back to the last segment of this review for test number 2.